Okay, how about now?
It's better.
Better? Okay. Okay, I'll take my laptop a little closer if that is helpful. All right, let me share the screen. Okay, let me share. Okay, that's not what you would like to see. This is the one. Okay. All right. 1 second. Let me just. Okay, so can we start now? Better than before?
Yeah. It's
Oh, okay, cool. I will start recording. Okay, cool. I hope will be better. Okay. I started recording, yes. Okay. All right, okay. So let's begin this chapter. So I was saying like your homework grade for homework 2 has been uploaded. Have a look. If you have any question, email it to me. As I say, like I have received a couple of emails from you guys. I haven't addressed all of them, although I have addressed a couple about like in homework 1 and 2. So if you have any query, anything that you're not sure about, you can email me. Okay, I will get back to you about your grades and anything. Your class test 2 grade is under grading, so it's with your grader, so it should be graded soon. Yeah, so let's see how does that go. Okay, so this is electronic grading and getting feedback and all that. We'll see how does that go. Okay? Probably I may share a Google Sheet with all of you that will say what points you have lost or whatever. Okay, so that will be self-explanatory. So yeah, we'll see. But then again, if you have any question, any confusion, you can always ask me. Okay, so let's start this chapter. It is called binary heap, which is very much related to the tree, the binary tree. So and it's very easy compared to what we have done with balancing and everything. This slide that I am sharing with you is already Moodle, so if you would like to download, go download it and have a read. Okay, and I would like to mention your third homework is related to heaps. Okay, so it is on the priority queue. So heap is a structure that we basically use to implement a priority queue. So we will talk about priority queue right after heap. I believe if I go through today's slide, and it is yeah, it is uploaded. So if you read and if you like go through your third homework, you should be able to understand like how to implement it. And I must say that third homework is the easiest one that you have got. Okay, so most of the stuffs are done already. You have to just implement some of the methods, and you have to just write down your own test files, and that should be more than enough. So I believe it's the easiest one. So okay, let's begin. Okay, so as you can see, a binary heap is a complete binary tree. It is a tree. So underneath there is this binary tree structure, but it is a complete binary tree. So if you remember the complete binary tree, up to the level before the last one, it is a complete binary tree. And it starts filling in the nodes starting from left to right, if you remember what complete binary tree is. Okay, so the heap will be a complete binary tree, and there are two properties that heap maintain. Okay, so one is called the order property, and the other one is the shape property. Okay, so underneath it is a binary tree, it is a complete binary tree, but there will be two properties that will be associated with heaps. One is order and one is shape. Okay, so we have already talked about the shape of the binary heap, which is, it is a complete binary tree. So whenever we are using a binary heap, if you mention it as a heap, it must be a complete binary tree. Okay, and the order, it depends on what kind of heap we are building. Okay, so how the data is ordered. Okay, so next slide, we'll talk about this. Let's go in there. Okay, so to talk about the order property, we must mention whether we would like to work with a max heap or min heap. Okay, so there would be two kinds of binary heaps, that is max heap and min heap. Okay, so what happens in a max heap, the value of a node, okay, in max heap, the value of a node will be greater than its children. Okay, I say that again. Well, you can see that in the slide as well. In max heap or in, okay, let me use the annotation. Okay, here. In max heap, you can see that a node, the value of a node will be greater than its children. Okay, so 100 is greater than 84 and 71. And that applies recursively. So 84 has a value greater than its children, which is 60 and 23, and it keeps going. Okay, so that is our max heap. So if you are thinking, oh, wow, okay, it's not a binary search tree. Okay, so just remember it is a binary tree, which is the complete binary tree, not binary search tree. You know the difference, right? The binary tree and the binary search tree. So the heap is a complete binary tree, not binary search tree. So if you are kind of like in there, well, how 71 could go on the right side of 100, that's totally fine, because we're working with binary tree, not binary search tree. Okay, and now in heap, it's just the opposite of max heap. The value of one node will have smaller value than its children. So if you look at the min heap in here, 1, okay, that is the root of the tree, and the values of its children are greater than 1, and that applies recursively. Okay, so yeah, as simple as that. Okay, so this is what a binary heap looks like. Okay, so it depends what kind of we are going to work with, max heap and min heap. So you now know the two properties. One is the order property. Now you know how the order matters. If you are using a max heap, the greater values will be on the, closer to the root, and it's the opposite in min heap. Okay, moving forward. It's a small chapter though. Okay. Now, heap operations, particularly heap operations. Insert and remove. There are just these two basic operations of heap, that is insert and remove, and it has some certain technique of doing that. Yeah, we are just working with two basic operations, insert and remove. Okay. Let's see how does the heap insertion works. Okay. Whenever any operation is taking place when we are working with binary heap, we must maintain the two properties of binary heap. That is the order property and the shape property. So we must keep in mind that if you're working with max heap, the value of one node must remain greater than its children. And at any point after performing the operation, it must remain as a complete binary tree. Okay, so we must maintain these two properties. Let's look at the example that how it works, and it'll be easier to understand then. Okay, so here, look at the example. So this is the tree that we have, okay? So 100 is the root and the values, and let's say we would like to insert a value 90, okay, in here. So you can absolutely tell that where the 90 could go looking at the values in the tree, which is either the left child of 100 or the right child of 100. So it may have these two potential spots in the tree, but let's see how it actually works, okay? So moving on to the next one.
I have a quick question.
Yes.
So I'm kind of confused. What exactly is a heap?
Okay, heap is a complete binary tree. Does that make sense? Do you know what complete binary tree is?
Mm-hmm.
Okay, perfect. So a complete binary tree where the values will depend on if you're building a max heap or a min heap. So it is a tree. At the end of the day, it is a binary, complete binary tree. And how the values will go, it depends on if you are working with a max heap or a min heap. Okay. So if you're looking at the slide that I have kept open now,
Mm-hmm.
so you can look. So the values in this tree, when we are working, if it's a binary heap, the values will be assigned the way you are looking now. So if it's a max heap, any node, the value of any node will have greater value than its children if it's a max heap. And if it's a min heap, the value of one node will have smaller value than its children. Again, it's a tree. It's a complete binary tree.
Okay.
Okay, yeah, so as simple as that. It is just a complete binary tree with some certain orders of values. Okay, so it will be clearer when you see the application where we actually apply. So yeah, but if you ask what is a heap, it is a complete binary tree in the first place. It is a tree. So same infrastructure as tree, branching, like the hierarchy, everything is same. It's a tree. Okay, so complete binary tree with some orders of values. Okay, just give me 1 second. Okay, no. All right, okay. So moving forward, now we are trying to see how we can insert value to a max heap, okay? So you know how to insert a value in a binary search tree, right? You know, you first run the method called contains. If it returns false, then you insert the value. You know, like you go in each node, you compare the values of its children, and you decide which branch to go, if you want to go to the left branch or to the right branch. So it has its own procedure of insertion when you're working with a search tree. Similarly, when we're working with binary heap, it has its certain procedure. Okay, so now this is insertion happens when we're with a binary heap. So in here, in this image, okay, you see that the 90 is placed as the right child of 23. Okay, so it starts from there. As we know, this is a complete binary tree. It starts filling in from left to right in a tree. Okay, so we had 137 as the children of 60, then to the next spot, which is the left child of 23. So 90 goes in as the right child of 23. However, if we would like to maintain the order property of the key, cannot be the right child of 23 because 90 has a greater value than 23. So it must go somewhere higher than 23. Okay, so as I said, whenever any operation is taking place in binary heap, okay, that must maintain the two properties that we have mentioned earlier. Okay, all right, so well, it enters to the tree as the right child of 23. However, that is not the right spot. Okay, here. Okay, so we have inserted the 90 as the right child of 23, but well, by doing that, we have ensured the shape property of the binary heap, but the order property is still broken. Okay, so we have to fix that. How do we do that? Very simple. We just compare the value that is 90 that we are inserting now. We are going to compare it with its parent. Okay, so 90 is being compared with 23. If the value of the child is greater than its parent, then we perform a swap. So that means the 23 comes down where 90 is and the 90 goes where the 23 is currently. So if you look at this, there is a shift up in here. Okay, so we kind of swapped and a shift up has happened. Okay, so 90 went higher and 23 came down. We will keep doing that until we find the right spot for 90. Okay, so we will repeat the same procedure. We will compare the value of 90 with its parent, which is 84 now. So if you compare with 84, you see that 90 has a greater value, so we will do another shift up. Okay, so there is a typo in here which calls shift up. I don't know what is that. It is shift up. Okay, so here. Next shift up, okay? So 90 goes at the spot of 84. 84 comes down to where 90 was. And we will do again the next comparison. So 90 is compared with its parent 100. And at this point, it is visible that 90 has a smaller value than 100. So it is in its right spot. Okay, so now that is done. So when we are at this point, we can say our insert operation has completed. At this point, the shape property and the order property of a max heap is how it should be. Okay, both properties are satisfied. Okay, both of them are here. So the insertion happens like this. Any question so far? Okay, just give me 1 second.
I have a quick question.
Sure. Okay. Yes, Emmanuel.
So, okay, so we just keep going until the parent is becomes larger than whatever we inserted.
You're right. Yes.
So then we don't what about the what do you call it? Like the nodes on the, like, for example, the nodes on the left child, like on the left side. Like, do we just not worry about those? We just keep going up.
Yeah, like you just compare it with its parent, because max heap, if you look at the previous example that we started with here. So in max heap, as I said, the value of any node will have greater value than its children. So if that
Okay.
order property is maintained, along with the shape property, which is a complete binary tree, then we're good.
Okay, gotcha.
Yeah. Okay. Any other question? No? Okay. Then let's look at how the remove works. Okay. So here is another example. Let's look at that before we go towards remove operation. Okay, if now we say that we would like to insert 41 to this tree, so you know where to insert, where to begin the insertion from, which is the left child of 12. We start filling in from left to right as complete binary trees do. So yeah, so 41 is there, but at the same time, we have to maintain that order property. So we compare the value with its parent, and we see that 12 has a smaller value than 41. So we do a shift up. And I believe that is the right spot for 41, because when it comes to the location here as a left child of 71, it compares a value with 71, and it sees 71 has a greater value than 41. So 41 knows that I am staying in here. Okay. So another example.
Quick question.
Yes.
So we're supposed to insert the whatever it is that we're inserting as the last child of the tree?
Right. So that's what you do in a complete binary tree, right? So you start exactly the last, like if you were considering it as an array, the last spot. Yeah.
So where would we, like, for example, in this tree right here, like, how did we decide to insert it to the, like, the right side or the left side? Like, what determines the last child?
So do you remember how complete binary tree fills in?
Yes.
Yeah, so it starts from left to right filling in. So if I say that, what would be, so now if I say that I would like to insert a value, let's say 50 in this tree. Okay, so just give me 1 second, I'll use this annotation. Okay, okay, so I would say that I would like to insert 15 here. How will that work? You do this small exercise. So if we want to do that, okay. So if we want to do insert 15 here, so what do you think where it will go initially?
Oh, go ahead.
No, you go.
Okay. I guess it will go to the right of the 12, and then 50 is going to go up where its children is going to be.
Okay, Ali, just give me 1 second. Just 1 second. I didn't write that on the right spot. Let me write it down in here, because that is our tree. Okay. All right, now here. Okay, so now where will this go?
First, it's going to go to the right of 41.
Yes, exactly. And how can you tell? Like, why not the left child of 29, let's say?
Because we go like left to right. So the left of 41 is already filled, so we got to go to the right. So after
exactly right. So does that answer your question, Emmanuel? So you know that you start filling in from left to right. So you're saying you just have one node, 5, and then you would like to insert 6 in it?
I think I know what they're confused. So the whole thing, like, I'm just like, look, you just look at the tree, and let's say you're gonna insert a number. If there's a left, it's gonna go right, and if there's a left and right, it's gonna go left to the another child. You know what I mean? So you're just inserting left and right. It doesn't matter the ordering or which number is bigger than another number, right?
Okay, I think, okay, I'll come back. I think where David is confused is, David, it's not a binary search tree again. So there is no obligation that if you have 5 and you would like to insert 6, it will be the right child of 6. Yeah, okay, I thought, because it happens, you know, when we kind of jump to binary heap from binary search tree. And yes, Ali was saying, so you start filling in from left to right. And if we are thinking structurally, it is super easy because it is kind of the end of your list. Okay, so you do not have to even find out, oh, okay, so what is that parent and where do I put that 41 or the 50 I would like to insert in here? It is simply the end of the list. You just insert a new element to the end of your list. Okay, so it is really simple. We will look at that, okay? Just bear with me. Soon we will look at the example with array in this slide, okay? So that will make things more, I think, easy to like think and consider. Okay, so we were saying that we would like to insert 15 here. If we do that, that would be initially inserted as the right child of 41. However, what will happen next? Okay, let me draw that. So it will initially be inserted as the right child of 41. Okay, why is that bad? All right, so if we would like to insert 50, it will go in here like that. Now what happens? Is the order property fulfilled in here?
No.
No, yeah. So yes, Jean-Dorel, thank you. No, yes. So what do? Is we compare 50 with its parent and then do a shift up. Okay, so basically the 50 goes in here and the 41 comes down. Okay, and then that is where it will remain, as 71 has a greater value than this. Okay, so this will be its actual spot. Okay, so I think it's somewhere clear for now, but yeah, as I said, like we will look at the array, like list version of it, and you should be able to understand. Okay. Now let's move on to the extraction. Okay, so the remove operation when we are working with heap is known as extraction. Okay, so here. So if you would like to remove an element from a heap, you can just remove it from one spot, and that is the root of the tree. Okay, so you can only remove your values if you are using a heap from the root. So we were working with a tree, like which was, I shouldn't say tree, we were working with a heap that has 100 as its roots value. So if you want to perform extraction, it will only extract the value of the root, which is 100. However, when that happens, obviously, we can say that the order property is broken, that we have to maintain. Okay. So what we do at this point, okay, so you see that the 100 is already, removed in here. So we must, there cannot be, it cannot stay like that, of course. So we have to substitute the value of the root with something. So how do we decide what to substitute it with? Okay, so of course, yeah, I think, so we are basically removing, we're extracting a value, so it must have one node less than the previous tree that we're working with. So there will be one node extracted, but at the same time, we have to maintain the shape property and the heap property, the order property. Okay, so here, what we do. So we extract the value of its root, okay? And we copy whatever we have as the last element in our list, okay? So if you're working as a list, okay, consider it as a breadth-first traversal. Okay, so you would be able to remember how the BFS works, and the list would be exactly like that. So 12 was the last value of the list, and we just copy 12 to the root, and you get rid of 12 in here. Okay, so we copied
Can I ask a question?
Yes, Bill.
So with the heap extraction,
Yes.
when we're extracting a number, we don't do rotation.
I can't hear you well, Bill.
I'm saying when we're doing extractions, we don't use rotations.
No, there is no rotation in here. Rotation only applies when we're working with tree balancing. Okay. Okay, so going back in there, 100 has been removed, it has been extracted, and the last value from the list is copied to the root, which is 12. You can see the image, and you delete the last child node. Okay, so we get rid of that, and as we have already copied that value to the root. Well, when we have done that, absolutely we can say that it is not a max heap. Well, we know how the order property works for a max heap, and 12 is a smaller value than many other values in the tree, so it is definitely not the right spot for 12. What to do now? Okay. We will form some shift down, okay? So we will compare, so if you look at the previous tree in here, so 12 was the root, and it has been swapped with 90, okay? So the 90 goes on top and 12 comes down. Here, something that you have to consider. Okay, so if you compare the value 12 with its children, okay, 90 and 71, you see in the next image, okay, it has been swapped with 90, okay. Why not 71? Because both are greater than 12, and we are trying to pull the greater values up, but why not 71, why 90? Anything that comes in your mind? Great, John Durrell, yes, excellent. Okay, so that's what we're doing. When we are comparing the value 12 with the values of its children, 90 and 71, we would swap the value of 12 with the child having greater value, okay? So definitely two children of 12, 90 and 71. 90 is greater than 71. Hence, we would like to swap the value 12 with 91, not 70. Because in here, in max heap, we always would like to bring the greater values on top of the tree. So If you swap it with 71, there is a chance that the tree has greater value at some point, and yeah, we have to do more shifting, okay, which we definitely wouldn't want. So yeah.
So the shifting down happens after removing the 100. So what if you wanted to remove something else in the tree, like a 41 or something?
Yeah, we'll do that. So if we let's just finish this, then I'll ask like what to do in the next extraction. Okay, yes. So here, okay, so the 12 is in here, so you can definitely tell that it is not the right spot for 12, given that it is a max heap. So you can you tell like which direction the 12 will go? Just don't look at the next slide. I know it's there, but
85 gotta be the place of 12, and 12 gotta go down, right?
Yeah, well, right. 84. Next step, it will be shifted down on the direction where 84 is, because 84 it has the greater value between the two children of 12. So 12 isn't there. However, that is not, again, the right spot for 12. So 12 goes one level down in here, and it is remaining as a leaf as the right child of 23. And at this point, we can say this tree has both the shape property and the order property of a max heap. Okay. Yes. Now, if you are using a heap, you cannot just say remove this value from this tree. Okay, so you cannot pass it as an argument of the method that remove 84 or 60 or 23 or like that. Okay, so you can only remove the value that is in the root currently. Okay, so if you would like to, let's say, remove 23, you have to wait until the 23 comes to the root of the tree. Okay, and you have to remove everything that has greater value than 23. Okay, so now you see the pattern, okay, which is very important, both these operations. Okay, so this is how the extraction happens. So if I want to do a next extraction, that will be 90. Okay, so if we want to perform extraction, that will be 90. It is similar, I wouldn't say same, but similar to the pop when we are using a stack, or the DQ operation of a queue. You just know from where you can remove. It's not the value, rather than it's the location of the data from where you can remove. Okay, and that happens in the binary heap as well. Yes, Bill, that is the final location for 12. That is where the 12 stays as of now. Okay. All right, so I don't know if there is any other example coming up for the extraction. Yeah, okay. So I believe you would be able to understand, but if still it's unclear, we will soon look at another entire example of this. So you should be able to understand that. If not, feel free to ask me questions. You can ask me questions now, regardless. But yeah. Okay. So where did this come from? Okay. That is done. So, okay, let's now try to understand how we can implement a heap. Okay. So, as I was saying, start considering it as a breadth first traverse and put it into an array, because you have recently worked with trees. Okay. Yeah. So look at the array in here, and you'll see that it is exactly a breadth first traversal. Also, there are some numbers assigned to each of this node, and it is simply the indices in the array, okay, of the location. So this is already a heap, okay? This is already a max heap. However, you will be given data that you have to build a heap with. Okay, so there is an example later in here too, but this is just a sequence. You see that 4 in here, right? So 4 is the last element in the array. So if you now would like to insert a new value, let's say anything, which will be the right child of 23, simply goes at the end of the list. Okay, so if you're using an array list, it's not a big deal. Okay, so that is how you do it. Linked list. Okay, yeah, so here.
So a heap is an array.
I'm sorry, what's that, David?
A heap is an array. It's not like
you can implement a heap with any kind of list. Just it's a tree basically. So if you would like to implement a tree with using an array list, array, or linked list, whichever works best. Okay.
All right.
Yeah. Yeah. So what is next? Okay, I think these are something that you do not need explanation. Here, I think you already know this, okay? So how you can access the parent of a node, or the left child of a node, or the right child of a node. I think I mentioned this when I was talking about the binary search or binary tree. So yeah. So you already know that a child link is null if the index is out of range. Okay, so there is no child. Okay, so if you do not find the link for that. Okay, here is a complete example. Okay, so here, physical view of adding 90. Okay, so when you are actually doing this using a list, how it will look like. So here is the tree, and here is your list at the bottom. Okay, so when you would like to add a value in 90, see, as I said, you will add it at the end of the list in here. And by using this formula, you should easily be able to find what is the parent's location of 90. Which one is 90's parent? If you do that math, it would be able to find its 4, okay, the 4th index, and you compare it with the value of this index and do accordingly, like whatever conditions. So if it's greater than its parent's value, just do the swap. Okay, just do the shifting. Okay, so moving forward here. So you see the 90 comes in the 4th location, 23 goes down to 10. And then again, using the formula, you would be able to see what is the parent's location of 90, and you'll be able to find it's the the first whatever location in the array. And yeah, so yeah, see, it's very easy. It's easier than, of course, the balancing and everything. Okay. Okay. All right. So if you would like to see that how it works with its computational complexity, both the insertion and extraction has log n, big O of log n. You can easily say, why is it like that? Because we are able to choose that half of the structure to traverse and to decide where it will go based on its value and location. Okay, so it's log n, which is excellent, okay. Basically, up to this slide, this is binary heap. There is nothing more about it. It's very simple, less complicated data structure. Okay, so it is actually a tree, but just with the structure, like the shape and the order of values, it has been it has a different what is that operations. Okay, and we can use this binary heap to implement many other things, or we can apply it to sort. Okay, so perform sorting. So up to this slide, like up to this slide number 21, it is talking about the binary heap, and basically this is what it is, okay? And from the next slide, it will tell how you can use a binary heap to perform heap sort, okay? That is simply a sorting algorithm. We have an entire chapter of sorting, although I don't know if you remember, I talked about at the beginning of the course that we will be covering some of the sorting algorithms. However, that is not the content that may belong to the data structure format, but it's still good to look at some of the algorithms, like commonly used algorithms, and just be able to compare their computational complexities and all that. So since we're learning binary heap, it's a good time to talk about the heap sort rather than waiting to start the sorting chapter and all that. So let's learn heap sort now in this chapter, and we will compare again the heap sort when we are talking about the other sorting algorithms. Okay, so we will compare that how efficient it is compared to the others that we commonly use. Okay, before I start talking about the heap sort, just would like to say, if you are sending queries about your homework, please first check your comment box, okay? So it should say what you have received and where you have lost points. So basically, I think I mentioned that in class as well, that for this homework, it was assigned to the test cases, okay? So basically, the test cases should be passed, and if like maybe one of them are failing, two of them are failing, so you will be using some certain points on that. I will share that rubric, like what is each test case is worth, okay? So the values, so then you can do the math easily, okay? I thought that your grader posted with the header, but probably it was a little bit complicated to post it that way. So if you had the header, you would have known like what each test cases is worth. So if you are like, let's say missing, like if one of your test cases not passed, you will lose like 3 points something. But yeah, I will post that. So you will have like a better understanding of that. And then if you see that, well, the test cases are being passed on my end, why it's not passed on the other end, then you can send the query to me and I can double check with that, okay? All right, let's continue on a heap sort. Okay. Okay, rather than just going through the text in here, let me show you the procedure. I will directly jump on to the example here, and we'll start from here. Okay. Before even saying that how the heap sort basically work, let's begin from the example. Like if you have, let's say, this list that you have in here, okay, this is the list in here, like this list, okay, this is raw data, okay, so you have collected this data that you have to first build as a max heap, okay, so if you would like to perform heap sort, first of all, you have to build a max heap. Okay, you have to build that. So how do we build a max heap from a given data, okay? I will do some class exercise next class as well, like what kind of questions you might expect from this chapter and how to answer them. I will give you some exercise that you can do. So yeah, but this is one of them. So maybe you will be given this data, let's say this data like this, and I may ask you to build a max heap or a min heap from this data. How to do that? How do you do that? Okay, so this is how you do it. So first data that we will be working with is 10. So when I just have one node, it is, so I'm building a tree, basically a complete binary tree. So we have to maintain that shape property and the order property. So I start with 10. Okay, oops, all right. Okay, so I start with 10. So see, I have just one node now. Moving forward, the next data in my list was 51. However, when you are building this, okay, tree, the location of the values in your array will be changed. Okay, so you see, when I first started, this was my first data that I received. Is my raw data, unprocessed data. Okay, 10, 15, blah, 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 whatever. So in next slide, when I am trying to build this heap, so okay, I don't know why is that happening. Okay, I'll keep going on because we don't have much time left for the class. Okay. Okay. Oh God. Okay. So yeah. So when we are building, so initially we started with 10, and now the next data that I will be working with is 51. Okay. So since this is a max heap, 51 should be the parent of 10. Okay. So if you notice in here, the value of the array is updated. So now 51 is in the 0th location and 10 is in the 1st location, which is slightly different than the one we had previously. I just have a quick question. Do you see that arrow that I'm using?
No.
Your cursor?
Yes.
Yeah.
Oh.
Sorry, I'm not.
Oh,
Yes,
yeah.
the cursor. That's more appropriate. Yes. Do you see that?
Yeah, we'll see.
Okay, cool. Okay, because it will be really stupid if I'm just using the cursor and you don't see it. Okay. All right. Okay. So here. Okay. So next data that we'll work with. So you see, like this is a very good slide actually. So the next data is it's bold, like the number 2 that we will work with. So you know that it will go as the right child of 51 and it will stay in there. Okay, because we're building a max heap again. Okay, so here now. Okay, the step by step implementation. I will follow you, like, let's say 2 more steps, and the rest you should be able to understand. Okay, so 2 goes as the right child of 51, and see the location remains as it is because of its location in the heap. Now it's 18, so it will go as the left child of 18. However, the location will change and the 18 will be the parent of 10. By this time, you should be able to tell how does that happen, okay? Because we are inserting new values, we are building a max heap, and you know how the shift up happens, okay, when in case of insertion, when it is a max heap. And next data that we'll be working with is 4, and the 4 will remain where it is because of its value. And then the 31 goes as the left child of 2 in here. Oops. Okay, in here, here will be the 31. It's very ugly. Just give me 1 second. 31 goes in here. However, you know how the shift up will happen because of its value. 31 has a greater value than 2, so 31 goes in here and 2 comes down, and thus the list gets updated every time. Okay, so yeah, and I'm pretty sure if you are going through the rest of the diagrams in the slide, you should be able to understand how it's working. Okay. All right. So I'm not going to explain all of them right now, but if you have any question, I can take them. Okay. Now that our heap is built, which is this, okay, this final tree in here, that is our max heap. Now we can start performing with, like, we can perform sort. Okay, we can do the sorting now since we have a heap sort. Excuse me. Okay, so we are calling it in place heap sort. What does in place mean is we do not need any extra like memory or location to perform this sort. we will be doing that in this list that we have right now as the max heap. We wouldn't need any extra spot, any extra memory for that. However, many of the other sorting algorithms need that extra memory to perform that sorting. Okay, but heap sort, it does not need that, okay? So yeah, that is why it's called in-place heap sort. So rather than just reading the descriptions, which you can clearly do by yourself, I will just go to the process. Okay, so I believe this is, yeah, so the image A shows the original max heap. Okay, this is where we begin our sorting from. What we simply do is we perform some extractions, okay? If you remember how we did extractions, okay, we always were able to extract data from its root. And basically, root has the highest value of the tree. So what we do, we extract the value of the root, and rather than just, removing it from the list, we keep it at the end of the list, okay? So we are not just removing it, rather we just keep it at the end of the list, okay? So we keep it at the end of the list. However, when we have done that extraction, okay, we structurally, when we are performing with it, we are performing the heap sort with a list, okay, we just reduce the size, or you can use a pointer or anything that will indicate the second last element as your last location of the list for your next iteration, okay? So rather than just saying this stuff, let me show you in here in this picture. So if you perform an extraction, the 64 goes out. So what you do at this point, you just extract 64 and like bring it at the end of the list, okay? So you bring it at the end of the list, and you know how does that happen? Like the last value in the list goes as the root, and you perform shift down and bring 23 to its right location, which is in here. So the 23 goes on top, so you compare and swap the value of 23 with whatever child has the greater value between these two. So you swap it with 51. So 23 comes in and 51 goes up. And then you do the same. I don't know why they didn't write it in here. The 23 should be in here written. Okay, so it should be 23 in here. Okay, and then yeah, the 51 should be in here. Probably they'd have done that in the next graphic. Okay, so 23. Then you do the comparison again with the child that has a greater value. So 23 and 18. So 23 and 90. The 29. Yes, they should be swapped. So 23 comes down in here, and 29 goes up. And after performing that extraction operation, okay, that we usually do, we have this tree in here. So if we are looking at the tree after extraction, it looks like this. Let's see here what has happened. So we have kept that value that we have extracted at the end of the list, and we are reducing the size of the list down to whatever, like less than 1 than it had previously, and this location will work as the last element of the tree now. So visually, the tree will look like this, but in the list, we are keeping the value since we are performing a heap sort in here. Okay, so moving forward, now we will perform again the extraction. So this time, it will extract 51 from the tree. So the 51 gets swapped with, I think, 4, or no, wait, was the last value? Yeah, I think 4. And yeah, 4 gets swapped. I will clear these numbers. Okay. Yeah, so 4 gets swapped, and 51 comes to that second last location. And yeah, this is how it keeps going on. So there is this slight change in here, like not change. This was wrong notation. I updated that. So what happens every time C? Okay, so the root always has the highest value when we are working with a max heap. Okay, so every time we are performing extraction, which is going at the end of the list, and when we keep doing that in the max heap, okay, the data will be sorted in ascending order, okay, every time. So the largest value goes to the end of the list, okay, every time, and it will make the data sorted, okay. So keep like go through this slide, okay. I have uploaded that already in Moodle.
So question?
Yes, question.
So the gray is like a separate sorted list.
I wouldn't say it's a separate list, okay. It is the same list,
like in code,
however,
though, like, so like you have your regular list and then you have a new one that you create, which is sorted. So you're kind of just like removing things and then throwing it into your second list.
I would say it is I wouldn't say a new list for that, okay. It's that old list that I had, except for I'm just updating every time the max size of the list, okay. So the gray part is the sorted part of the array, okay, that we have already worked. Okay, Russell is saying something. Yeah. Yes, exactly. Yes, Russell is saying that is why. So it is, so due to this method that we're applying with a max heap, we are showing that we do not need a new list for that. However, as I mentioned earlier, many other sorting algorithm uses that new list to sort data, which you do not need for the heap sort. Okay, just look at that, take some time. Okay, I can take more questions next class on this. I have a quick question if you can answer. What would you do if I say, if you would like to perform a heap sort to sort the data in descending order? What do you do? Anything come?
Extract the smallest one first.
And for that, what do you have to do? Because you can just access like the root. Yes, Russell, awesome, yes. You have to first build a min heap, okay? Instead of max heap, we will be building a min heap and then perform extractions exactly the same way that we are doing here. So the heap sort portion will be exactly the same. We will just apply extractions in here. However, we have to build a min heap for that. Okay, awesome, excellent. Okay, so if you have not already recorded your attendance, please do that. But before you remove, just stay a little longer so that, I don't know, there should be an option of record attendance in Zoom. I'm just looking for that. I don't know where it is. I don't find it. I wanted to record it in here. Okay, I don't know what is that. Okay, I cannot find that. I will look into that. Okay, you guys can, I think you guys can also annotate from your end. I don't know, like, yeah, I have to explore it a little bit, then I think we can utilize all the options. Okay, so that's it. Okay, so just record your attendance, log your attendance in Moodle. You have just like 4 minutes left to do that. do that before you exit. So I will upload this lecture. Also, it'll be great if you share the link for today, and then I can give you update for the next class. Okay, so next class I will just work, like we'll do some example, okay, and how to work. And
where is the attendance look?
what's that? I'm sorry?
Where is the attendance on Moodle? I'm trying to find the link for the attendance for today.
Okay, it should be under your attendance. Okay, I showed you in the last class
Okay,
how to get
yeah.
into that. So just go into the attendance, it should allow you. Yeah. Okay. Okay, all right. So I'll see you next class. Okay. All right. You're welcome. Stay safe, guys.
Have a good day.
You too.